All right. Good morning, everybody. I just kind of want to give a brief preface as we're going into this. Today we're talking about sheaves, and really the definition of a sheaf and pre-sheaf and that stuff, and some examples and exercises surrounding them. Um, as we progress further into this book, you know, I kind of want to make the point that I've read some of this stuff. I've read further ahead in Vakil than where we're at now, but I don't feel super confident with it. And so there kind of might be these like long, awkward pauses where I'm like thinking through something. Um, and so for the sake of me not feeling nervous or anxious about having that happen while I'm on camera, I just want to give the disclaimer now that one, that's going to happen, and that two, I'm an undergraduate who really I don't know what I don't know, and I have a proclivity to say things that are wrong. Um, so if you're watching this and I say something wrong and I don't correct myself, please comment in the comment section, so that I can understand it, because that's kind of how you learn. Um, and then yeah, just feel free to skip around based off of where I'm just pausing for a long while to think about things. Yeah, we're studying some pretty deep stuff, and it's very important that we take it slowly. So, okay. Um, so yesterday we ended with like introduction to sheaves, and obviously we've talked about them before in the context of the paper that I wrote on sheaf cohomology, the expository one. Um, and so we had kind of said that our example of a sheaf was the ring of smooth functions on an open subset of a topological space. Excuse me. And that basically we should be able to have restriction maps like so, and then we should be able to glue on intersections of restriction maps. And so our kind of picture of this was that in the yellow highlighted sections, since our functions agreed, um, then we were able to glue F1 to F2 to F3 to F4 to F1. And so I'm going to just make a bold claim kind of ahead of all of this, is that this construction of restriction maps, in this case to the orange, green, blue, and purple subsets, right, that is a pre-sheaf. Um, so the whole pre-sheaf business is like setting up the open subsets and inclusion maps between them. And then the sheaf data is like actually gluing things to and telling you how to glue them, right? So, one thing I've been thinking about recently that I don't know is true, but like, you know, if a sheaf is really just this collection of things, and then a sheaf tells you how to like glue them together on certain like intersections, is there like a topologically invariant definition of a sheaf? Because the one that we're going to end up using uses the notion of like putting a pre-sheaf of finite abelian groups on something. And I don't think that those require, um, I don't know, because a pre-sheaf is technically on a topological space. So I don't know. Anyway, we're going to go a little bit sideways from that today. We're going to talk about the germ of a smooth function. We've talked about this in Hartshorne, in the context of, so definition, germ of a smooth, that had three O's. Can you tell it's 7 in the morning? Um, Germ of a smooth function. So in Hartshorne, we had talked about this as U and phi of U under the equivalence relation that U phi of U was congruent to V and phi of V. Nope. If and only if phi u equals phi v on u intersect v. And I'm pretty sure that Vakil uses the same definition, except he does it at a point, and then he says we'll find an open set around the point. Yeah, so this is kind of the Hartshorne definition. The Vakil definition is that a germ of a smooth function is of the form f and u with a point p in u, and then f in the ring of whatever we care about on u, either smooth functions or regular functions. With the same relation that f u is congruent to g u if there exists some open set w contained in u and v with p and w such that f is equal to g on w. And I'm pretty sure that these are equivalent definitions because really the set that he's talking about that's open.
Where does v come into this?
Oh, thank you. That's where v comes into this.
Okay.
Great question.
I got a little confused for a second.
Yeah, so the main difference between these definitions is that, I guess topologically speaking, right, we have the axioms of a topology, tau on a set X, is that basically tau is collections of open sets of X or subsets of X, and that one, the whole space X and the empty set are open in tau, and then that arbitrary unions of open sets are open. And that finite intersections of open sets are open. And since this is certainly a finite intersection in the first case, right, like if we have u and we have v, then this business in here must also be an open set in the topological space. And so really the condition is that if you have P in both U and V, then P also has to be in U intersect V, and so then this is just the same open set that Hartshorne defines, right? So if you condition this whole thing is that the germ of a smooth function at P, and you find your two open sets, then not only is this thing going to be an open set, but it's going to have P in it. So in such a way, these things are these definitions are the same. I will say I kind of like Hartshorne's better, but maybe it's just because I've been using it longer. Like frankly, I just kind of didn't use Vakil's definition here. So in other words, two functions that are the same in an open neighborhood of P have the same germ. We call the set of germs the stalk at P, and it looks an awful lot like the local ring at P, because of course it is. So this is the local ring,
How are
at
we?
P.
How are we denoting it? Is that O or
Yeah, it's the script O for the ring of
oh?
either smooth or regular functions, depending on your preference.
Okay.
Um, so local ring at P is equal to stock of germs at P. Um, and then yeah, note that the stock is a ring. You can add two germs and get another germ. If you have a function F, then you have function composition. Um, if P is in U, you get a map from uh, O of U as an injection into the local ring at P if P is in U. Um, and really, like we talked about this in Hartshorn, but this also goes into K of Y, right? So like this is kind of we're doing stuff that we've seen before. um, Although admittedly, I kind of wonder. Like I haven't ever looked back and like rewatched any of our lectures. But I kind of wonder like if I really understood it when I did it then or if it was like it just needed a few weeks to sink in. It's kind of one of those things that's like there's so many videos up on this channel now that I get a little worried sometimes that it's like what if I said something very stupid? um because that happens a lot. Um
What's the policy with error counts on videos?
with what?
Error counts on videos.
Um that's a good point.
That's
I
just
don't
a
know.
joke.
If you feel like going back for it, maybe I'll get like donuts at JMM for everybody.
Yeah, I'm not. I'm not going back.
Um,
That's 32 hours of video after this.
Holy cow. Dude, we've been putting in work.
We have.
I'm proud of us. This is great.
Yeah. Yeah. Thank you for
Um,
doing this.
of course. I mean, I want to learn this stuff. This is,
Yeah.
to be honest, like the only reason why I'm really videoing this stuff. I don't think this is ever going to help anybody else because I'm just not, I don't know enough, right?
Right.
But I'm doing it because otherwise my brain will be like, I'm tired. I want to stop. And I
Yeah.
can't have that happen because every hour of break is precious time that I don't have during the school
Right.
year.
Right.
And so like this time is just my safe time to kind of get things done. So I'm
That's fair.
recording everything not because I think it's like my voice matters about any of this, but it's really more of a I need to force myself to lock in. And recording yourself does that.
Yeah,
And
that'll,
also, I guess it's nice because I can look back and be like, oh yeah, I did that, or maybe I can show like for grad school admissions, like, oh yeah, I was like studying this stuff.
right.
But yeah, um, yeah, OP is a local ring. Um, and we can definitely consider the germs vanishing at P. Um, so consider germs vanishing at P, i.e. the functions defined on the open sets go to zero at P. Um,
Hmm.
then they form an ideal, um, which is I can't ever draw. There's like this exclusively uniquely German font for M. It's called \mathfrak, and it looks so cool. I can't draw it. But MP. So MP is going to be the maximal ideal of germs vanishing at P. Um, Namely because when you add two things, they still vanish at P, and then when you add two things vanishing at P, they also vanish at P when you add them. And then when you multiply anything in, you're multiplying some number times 0, and we're working over an integral domain, and so it goes to 0, so it's an ideal. And so this is the maximal ideal of germs vanishing at P. And we check that the ideal is maximal, not by doing anything constructive, but by showing that the quotient ring is a field, right? So proof, so OP quotient MP has, this should be isomorphic to R. And let's figure out why, because he just kind of says proof by commutative diagram.
Well,
So, okay, let's look at, I'm going to say that this is our claim. So then OP,
is MP contained in OP?
yeah, it is. Because it's germs vanishing at P, and OP is the ring of germs
Okay.
on open subsets containing P.
Yeah.
So this looks like basically U comma F plus the equivalence class of script V, just regular V, comma 5V, where this thing vanishes at P. And P in both U and V. And so really we have the case whereby
We saying
first
that F is equal to 5V?
yeah, I mean, yeah. Yeah, like it's in the equivalence class. Or the way I kind of wanted to go with this is first isomorphism theorem. We have this thing going into something, and then we have this equivalent thing going like so. And then the thrust of it is that if this is psi, right, we have that the kernel of psi is exactly equal to MP. So we really want to construct a field that's an injection of OP and has kernel of MP. And we've, of course, claimed that this thing is R, but we have not proved this yet. So I'm just going to say not given at all. So how can we bridge? I guess so the morphism that Vakil suggests is that define psi to go from OP into R by F gets mapped to F of P. And again, since we're not working with regular functions, but rather with smooth functions, I think that maybe we pull some properties about that out. I don't know. So obviously we have the things that zero out. This clearly has kernel of things that zero on MP. That's true. I don't know how to get. I guess it's really not R necessarily, but it's rather the residue field of whatever we're working on. Like if we are working on R and we're looking at real valued functions, um, then this will be R. But like if we were working on some other field, I don't know that it would be isomorphic to R. Like if we were considering like complex algebraic geometry, then this would be C. Or just the residue field. Hold on, I just need to blow my nose real quick.
Okay.
Okay.
Bless you.
Thanks. And then the exercise is to show that this is the only maximal ideal of OP. And the hint is to show that every element is invertible. And it's because I guess you can divide by zero, or like you won't divide by zero by taking one over something in the quotient ring.
Oh yeah.
Um, Obviously this is not really a proof. I'm just gonna write sketch in here. But we'll put a dot 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 in a box and yeah, I was watching this funny YouTube video last night about like methods of proof, except you don't
Yeah.
prove the thing. It goes on for like 5 minutes because he's got a lot of funny examples. Then he starts getting to like some real life examples that he's seen like in grad school. And I think my favorite one is proof by so and so knows this, but I can't contact him for the proof. And so apparently there was this guy who had been like a master's student who had proved this thing but never shared the proof with anybody. He was just like, oh yeah, I know that this is true. And like it'll take too long to show you the proof. And
Yeah.
so everybody in the department accepted it as kind of like an axiom that the thing held, but they couldn't prove it and they didn't know how to contact the guy because he had finished his master's and gone off to industry and like wouldn't respond to emails. um, so yeah.
Yeah, there you go.
Note that we can interpret the function at a point or the value of a term at a point as an element of the local ring mod the maximal ideal. This doesn't work for more general sheaves. It does work for sheaves of functions. This will be formalized in the notion of a locally ringed space. There's a very important aside here that I wish Hartshorne had had an equivalent of. um, in his book, that the the maximal ideal at P mod the maximal ideal at P squared um, is a module over the residue field of OP mod the maximal ideal at P. In this case, it's real. Um, and this is called the cotangent space. And it's all of the linear functions which vanish at P, right? Or rather, all of the germs with total degree 1 that vanish at P. Um, and so, like, the kind of thrust of this is that if you want to, like, another way to think of the blow up of a variety, like, you can characterize that with the cotangent space. Um, so, yeah. Um, yeah. So, on to some formal definitions of sheaves and pre-sheaves. So, to be concrete, we will define sheaves as sets. However, the definition in the category of sets, you can be replaced by any reasonable category. And other important examples are abelian groups, K-vector spaces, rings, and modules over a ring, and more. You may have to think more when dealing with a category of objects that isn't sets with additional structure, but there aren't any surprising complications. In any case, this won't be relevant for us, although people who want to do this should start by solving a certain exercise. Sheaves and pre-sheaves are often written in calligraphic font. The fact that script F is a sheaf on a topological space X is often written as script F down to X. So I guess, oh, it's not an arrow. It's just this. Um, okay. Kind of a weird remark, but so, we'll start with the definition of a pre-sheaf. Um, there's a lot to it, but it's not actually that bad.
Yeah.
Uh, so a pre-sheaf script F on a topological space X, and again, I do really wonder, like, is there an alternative way to define this where it doesn't require an induced topology? Is the following data. So has for every U, which is open X, there exists U, or script F of U, sorry. F of U. Um, the elements of F of U are called sections of F over U. So the section of the pre-sheaf over U, alternative notation for this that becomes very important and that we'll know from homological algebra is that F of U is also, is it the zeroth? Yeah, cohomology of U over script F. So when we're talking about the cohomology of sheaves, this is the zeroth cohomology group. It's like just kind of where we start. And this is also equal to gamma of U comma F, which is the global sections functor, which sends local sections to global sections. And it's kind of how we generalize like local to global data. And then like I showed in my paper the other day, this is like just one step away from establishing sheaf cohomology. Sheaf cohomology is just looking at the right derived functor of gamma because gamma is a left exact functor. So we're looking at the failure of right exactness of gamma, and that is the same thing as the ith cohomology group. Hold on, I need to blow my nose. All right. Goodness, I almost keep knocking my Red Bull over. In addition to this piece, for every inclusion U into V, which are both open in X, there exists a restriction map res VU defined from the section on V to the section on U. And this is literally just like an embedding. Um, Oftentimes we're going to write this as just F restricted to U. Um, as kind of like a subpoint of this, is that like res U is the identity on the section containing U. And then the third point is that these things commute. So if we have, an inclusion of open sets U into V into W open in X, then the following diagram commutes and the maps compose the way you want them to. So F of W can be restricted straight down to F of U in the natural way. Or sorry, that goes to F of V and then it goes down to W. I always do that wrong. I always think left to right, but it's really down. But yeah, F of U. And then of course the natural like thing here is that you can go straight down to U. So this is by res WU. This is res WV. This is res VW or VU. Right. So res VU composed with res WV gives you res WU. I need to blow my nose again. Okay. So they have a funny exercise in here. A pre-sheaf on a topology in the category of open sets is the same as a contravariant functor from the category of open sets to the category of sets. I don't really want to work through that. I'm not that good at category theory. I yeah. But it's an interesting note. If you really love categories, maybe do that like on your own time.
Really love
Um,
categories.
yeah,
That's
I
funny.
I will say there's something like we haven't done kind of the philosophical side of category theory. We've just kind of been using it in an applied sense.
Oh, okay.
Applied being a very, very misused word here. The category theory hole goes a lot deeper, um, and it gets very much into stuff that I don't know about and that I don't feel comfortable talking about because I don't know anything about it.
All right.
Um, so what we've covered is kind of how to use some things in category theory, but like we haven't proved anything about like how the axiom of choice, for example, changes our notion of categories. Um,
Hmm.
and in general, category theory is built constructively, so no proof by contradiction, and then also without ZFC or the Zermelo-Fraenkel axioms, which are equivalent to the axiom of choice.
Yeah.
Um, and I don't know any about that. And so I don't know. I would just encourage you. There's a lot of math out there, and we're both very young.
Yeah.
We should be focusing on the more down to earth stuff. There's no need to get into like the deep end of category theory just yet. If you're using it for
Right.
something, then it's a perfectly reasonable thing. Otherwise, I would maybe wait until grad school to get into like the really nitty gritty of it, unless you want to go into mathematical logic, in which case, Dr. Brown in our department is a wonderful person to talk to. She's a mathematical logician. I had the pleasure of TAing for her a few years ago. Great, great person. So anyway, all of this to say, we're gonna avoid that one.
Right.
So definition, stalks and germs. So we'll define um, the stalk of a pre-sheaf at a point can be defined really in two ways. One is just as like a hands-on thing, where we talk kind of about gluing things together, I think, if I had to guess. And then the other way is as the co-limit of a category. Um, so the stalk of a pre-sheaf F at a point P. So at a point P, and I guess I need to add in the script F. Stalk of a pre-sheaf F at a point P is the set of germs of F at P. Um, and so this is literally the same definition as the local ring at P. What? Okay. Germs correspond to sections over some open set containing P, and two of these sections are considered the same if they agree on some smaller open subset containing P. Oh, I see. Okay, there is a slight difference that makes it worth writing out the definition again. So FP is equal to the same thing that we've been seeing with like F and U, which is open in the topological space such that P is in U, F is in the sections on U, right? And then
Hmm.
FU, similar to GV, um, if there exists W, or I guess P and W open in X, such that the restriction map of U comma W of F V comma W of G. And this is like very similar, but this is in sheaf notation. And it sets up very quickly kind of the gluing idea. I mean, the gluing idea was pretty obviously there before, but it's just
Yeah.
like slightly different. Equivalently, uh, the stalk at P is the colim of the section. And I don't feel like working through what that really means. But if you want to on your own, you're welcome to.
All right.
The general value of a section at a point doesn't make sense unless it's a locally ringed space. That's an important thing. Okay, so now we can finally define sheaves. So a pre-sheaf F is a sheaf if we have two axioms. Um, so one is called the identity axiom. And it's that for every open set U, if UI is an open cover, open, and I should add this U is open in X. UI is an open cover of U, and F1 and F2 are in the section on U. And the restriction map of F1 at UI is equal to the restriction map of F2 at UI for all I. Then F1 is equal to F2. So the idea is like they don't have to I guess they do kind of have to agree, don't they?
Mm-hmm.
I don't know. I'm
The
trying to think of like how this wouldn't just mean that it's the same thing on all of you. And I think it might
yeah.
mean that exactly. I'm just trying to make sure that it's not. Let me write down the second thing. So this is called gluability. So again, taking UI to be some open cover of U, if we are given Fi in the section on UI, for all I, such that F1 restricted to UI is equal to F2 restricted to UI, for all I. Oh, nope. Nope. I just rewrote the wrong definition. Sorry about that.
No, you're good.
For all I such that, and then Fi restricted to UI intersect UJ is equal to Fj at UI intersect UJ. Um, for all I and J. Then there is some F in the section on U. with the restriction map of F restricted to UI is equal to Fi. And this is a lot of notation, but this is basically the picture that we ended with here. Like we're given an open cover of our space, and then we look at the intersections and things agree on the intersections, and we have this big function that agrees, like just looking at F4 on the whole open set, that also agrees on the intersections of open sets for all of them, and we can glue things together in that way. In mathematics, definitions often come paired, so like at most one or at least one. In this case, identity means that there is at most one way to glue, and glueability means that there is at least one way to glue. Yeah, for experts and scholars of the empty set only, an additional axiom sometimes included is that the section over the empty set is a one-element set. And in general, for a sheaf with values in a category, the section over the empty set is required to be the final object in a category. For example, if U and V are disjoint, then the section over the union of their sets is the product of the sections. And then that basically factors through the fact that the section over the empty set is the final object. The stalk of a sheaf at a point is just its stalk as a pre-sheaf. The same definition applies, similarly for germs of a section of a sheaf. As a remark, an important exercise, pre-sheaves that are not sheaves. We can find that the following are pre-sheaves on the complex plane with the classical topology, but are not sheaves. Bounded functions, and then these things called analytic functions admitting an analytic square root. That's a very interesting example. So bounded functions, I guess, really don't have to agree. And so you miss kind of the identity axiom of gluing. And I guess of the subset of them that are bounded and entire, meaning that they are this thing called analytic that I won't go into, they're constant functions. And so you just kind of can't glue them, I guess. Um, a thing that's worth noting about sheaf cohomology is the two axioms for a pre-sheaf to be a sheaf can be interpreted as exactness of what's called the equalizer exact sequence. So if you have X going to the section on U, which goes into the sections on your open sets, which are the open cover of U, then you can kind of look at this in terms of two morphisms, F UI, F intersect J, where the identity piece is exactness here. So exactness here equals identity. And then glueability is exactness at oh, did I not draw the product in? Bro. I'm not. Okay. Wow. Um so product. And here exactness here is equal to glueability. Um and so when we talk about basically the cohomology of sheaves being the failure of glueability of a sheaf, then we're looking at the failure of exactness here. Equivalently, we're looking at the failure of right-derived functors to be right exact on gamma, which is the global sections functor. If you want to read more about that, again, you can take a look at my paper. It's pretty much at your level at this point.
Okay.
So I don't know. This is kind of a cool exercise, or not even exercise, but just remark. Um, so yeah. Um, yeah. I need to blow my nose real quick, and then we're gonna go into some examples of sheaves.
Okay.
All right. Um, okay. Important example.
Mhm.
It's called restriction of a sheaf. So, let F be a sheaf on X. I guess let's just write this as X. Here. And U be an open subset of X. Um, define the restriction of U, of F to U. Um, to be the collection um, of restriction maps FU of V equal F of V, where V is an open subset contained in U.
Change an X or you?
I think it's just that it's a sub-open subset.
Okay.
Um, then the restriction is a sheaf.
we aren't proving that.
No, I mean it's just it's like a sub sheaf.
Oh, okay.
So maybe we should. Oh, oh my goodness. That was why you were asking that.
Yeah.
Um, my bad.
No, you're good.
Um, yeah, no duh. Yeah, that's a very reasonable question to ask. Yeah.
And then you said, "Oh, it's a open subset." So I'm like, okay, that means it's an X. I mean,
Yeah, it's in you. It's in you. And now the question makes a lot of sense. Okay. Yeah. We'll define the skyscraper sheaf. So let X be a topological space and have a point P in it. And let S be a set. Um, let IP define from P to X be inclusion. Um, then what? Okay. Then I P comma asterisk of S of U. Holy cow! It is raining so heavy right now, out of nowhere.
yeah, it's been raining like that for me.
There's like branches of trees falling down.
Jeez.
Man, a sheaf of those stalks would give such a good cohomology. Anyway, this is a piecewise function that gives you just S if P is in U. Um, and the identity if P is not in U. It's worth noting that usually S is not a set, but rather a group.
Mhm.
And so the skyscraper sheaf is on a group support, and this is supported at P. Um, and for sheaves with values in a category more generally. This notation is admittedly hideous, and the alternative is equally bad. That's pretty funny. So yeah, it's basically the idea that it's like supported at P. So it's the skyscraper sheaf. It's all at P if it's in the open subset, or it all falls down when we're not at P. I'm gonna blow my nose again.
Okay.
So I just kind of want to take a second to look through the rest of the examples and see if there are like any unimportant ones. Or ones that I can just talk through. I know that there's one that's very important.
Mm.
Um, damn, all of these are important. Okay, on the one hand, it's a really well written book. On the other hand, yeah, I don't know. So constant pre-sheaves and constant sheaves. Um, basically, you can just define like the same idea of the skyscraper sheaf, except for you can remove the notion of P. And so you can just say that S of U is equal to S for all open sets, and this forms the constant sheaf. Um, sorry, it's a pre-sheaf. This isn't in general a sheaf. It may be distracting to say why. Lovers of the empty set will insist that the sheaf axioms force the sections over the empty set to be the final object in the category, i.e. a one-element set. But even if we patch the definition by setting the constant pre-sheaf to go over E, if S has more than one element, and X is the two-point space with the discrete topology where every subset is open, you can check that it fills glueability. Yeah. Okay. So it's really the constant pre-sheaf. Uh, okay. Exercise that we might decide to glaze over. Um, let F of U be the set of maps from U into S that are locally constant. Um, i.e., for every P in U, there exists some open set V, which is open in U, where, I'm just going to call the maps F. F of V is constant in S. And then show that this is a sheaf. And this is called the constant sheaf, but we'll probably call it the locally constant sheaf. And it's denoted by S with an underbar. It's a very funny notation. Um, okay. Well, we want to show, I mean, I guess we're given that this is a pre-sheaf.
Hmm.
I'm going to assume that it's a pre-sheaf. Proof by undergraduate math. Um, um, yeah, I guess let's do, so starting with the identity axiom. So, um, let UI be an open cover of U. Um, and then and let F1 and F2 be in the section over U with F1 restricted to UI is equal to F2 restricted to UI for all I. Show that F1 is equal to F2. And then we'll have to show glueability right after. So these are the set of constant maps such that for each of these things, right, when we restrict F1 to UI, then we're going to say, well, for F1 restricted to UI, containing P, and I guess this really includes F2 restricted to UI. There exists a neighborhood V, which is a sub-open neighborhood of UI, with F1 of V is equal to F2 of V is equal to some constant S. I'll say A and S. And I guess the idea is that this holds for every such P. This holds for every P. And so F1 is equal to F2. And basically they just jump around to be locally constant, but it's just kind of like this sort of thing. And then I guess for part two, for glueability, then keeping the open cover, let Fi be in the section on UI for all I. With the restriction map of Fi, wow, wow. The restriction map of Fi is equal to the restriction map on Fj. For all I and j, show that there exists F in the section on U such that the restriction map F to UI is equal to F sub I for all I. And so let's see. So for each point in UI, so let P be in UI, then there exists V, which is open in UI, with Fi of V. I guess let me put P in both UI and UJ. With Fi V equal to A equal to Fj of V. Or I guess it doesn't have to be V. We should put W also open in UJ. And then they definitely don't have to equal the same thing. In this case, if Fj equal to W. No, they do have to equal the same thing, right?
Yeah.
It's in the same. Hold on, let's look at the definition. So we get a P in U. We get an open subset where it's constant. Does not have to be the same thing. But then we need Fi restricted to UI intersect UJ to equal Fj restricted to UI intersect UJ. And since P is in both, then this is equivalent to Fi restricted to UI, or sorry, restricted to V intersect W is equal to Fj restricted to V intersect W implies that A is equal to B. And so then without loss of generality, Fi equals Fj on V union W. I don't know what the specific F that we need is, but I know that we're close to it. So we're trying to find the one function that encapsulates all of this behavior. I really want to say that it's just F is equal to A on UI.
Yeah.
Right, but I feel sketchy about that. I feel like that might not be true.
But that makes sense.
But does it make sense because it's convenient, is the question. Is there a convincing argument for why that is the function?
Well, I mean,
F restricted to UI is equal to A is equal to B.
for all I remember that.
Oh, that's very true. Yeah, for all I and for all J. So I guess it should be let's call this AI, AJ, AI, or sorry, BJ. And then let's have I think I know what the function is. It's a piecewise function. And it'll be AI BJ if um,
I is equal to J.
no, if P is in, like, okay, the picture that we're getting at here is if this is the thing and this is UI and this is UJ, then we have some P in the intersection where we have like a blue bubble, and then we have, I guess the blue bubble can go kind of anywhere. And then the purple bubble can similarly go kind of anywhere. And then in this intersection, we get that we have, Fi equals Fj equals, A. I equals AJ, or BJ. But then this extends over here too, right? So this also gives us like and so then we want to say, okay, given like maybe a different P, like a P prime, we get some other open neighborhood. Right? And this is all still within UI. This overlap is in the same overlap, right, as an open neighborhood containing P. And so we know that the function evaluated here is also going to be AI. And so then it glues over here to be AI everywhere.
Okay.
And then if we pick a point, so this is now like this neighborhood, but it really gets extended on to this whole business. Then for everywhere in this open neighborhood, we can pick another point like P double prime, and now we get like another open neighborhood. Let's use green. And we do the same thing, and we get added on to it this like area where we also get the constant function AI.
Yeah.
And so by pushing around these open neighborhoods, we get just the constant function everywhere. And so I was wrong, it's not a piecewise function. It is, in fact, the constant function. Does that seem okay?
Yeah.
I think I'm okay with that. I think that
Yeah.
this is a satisfactory, like, proof by picture for what's going
Yeah.
on. Okay. As another important exercise, morphisms glue. So let Y be a topological space. Show that the set of continuous maps to Y form a sheaf of sets on X. More precisely, for every U open in X, then we associate the continuous maps from U to Y. So, okay, let f from X to Y be continuous. Then for every V, which is an open set in Y, there exists U in X with F inverse of V is equal to U. So this is the definition of topological continuity. I think we've talked about this, right?
Yeah.
Yeah, okay, you are familiar with topological continuity. I just know you haven't taken topology, so I don't want to like pull out a definition and you're like, where the hell did that come from?
Huh.
But yeah, so inverse images of open sets are open. That's our definition of continuity. And then I guess this is going to be so much work. This is like 7 things. All right. What do we need to show that it's a pre-sheaf? Well, to get a pre-sheaf, we need sections of continuous maps established to their open sets. We have that. We have, if we have an inclusion map from one smaller set to a larger set, then we have a restriction map. That is also the case. And then if we have a chain of restriction or a chain of inclusions, we can also get a chain of restrictions that commutes. And I think that we're basically given that, right? Like if you have, the inverse image of V is X, but X contains W, which contains V, which contains H, right? Then we can restrict things down to W and H. So then what else do we need? We need identity and we need gluability. So for every U, if we have an open cover and we have 2 functions in the section, then if the restriction map for a piece of the open cover is the same, then the 2 functions are equal. This one might be tougher. So we want to show in the first case that for every open set U in X, if UI is an open cover, and F1 and F2 are in the section over UI with F1 restricted to UI is equal to F2 restricted to UI, then F1 is equal to F2. So, the sections on these UI are going to be the sections of continuous maps. Um, hmm. Hmm. So we're given F1 and F2. So given, let me switch to green. So given F1, F2 from UI to Y, then F1 UI is equal to F2 UI. Then for F1 inverse of V is equal to UI is equal to F2 inverse of V is equal to UI. Means that I guess we should call that V. This doesn't feel like something that's true, which makes me wonder if I'm interpreting the problem wrong.
Yeah. I'm not sure.
Because, like, it feels like it should be so easy to set up a counterexample to this.
Yeah.
Um, hmm. Kind of thinking that maybe we pick this up tomorrow.
Sounds about
My
right.
brain's getting a little burnt out. Um, I think I've been taking in too much new information. Um,
That's fair.
I think I need to sit with this and really think about it, and
Yeah.
we'll pick this up tomorrow morning. So
Okay.
I'm gonna go ahead and stop the recording. But yeah, so today was just kind of more sheaves. So
Yep.
all right.